1 minute. That's roughly how long it took for a routine graph to turn into a genuine scientific mystery. A team of astronomers wasn't even looking for it. They were studying something else entirely, tracking the motion of stars inside one of the oldest star clusters near our galaxy. And then, almost by accident, a gap appeared in their data. A blank space where stars should have been and simply weren't. No warning, no hypothesis waiting to explain it in advance. Just an empty band cutting straight through a graph that was supposed to look smooth and continuous. That gap came from the European Space Agency's Euclid Space Telescope, and it's just the latest in a run of genuinely strange, genuinely unexplained images this observatory has captured in 2026 alone. Tonight, we're breaking down exactly what Euclid found, why scientists weren't expecting it, and what it might mean for how we understand the life cycle of stars themselves. Let's start with the telescope doing the looking. Euclid launched in July 2023. Built by the European Space Agency with contributions from NASA, designed with one overriding mission: mapping the structure of the universe to study dark matter and dark energy, the invisible forces believed to make up roughly 95% of everything that exists, despite the fact that neither has ever been directly observed. To do that, Euclid needed something most telescopes don't prioritize: an enormous field of view combined with sharp, space-based clarity, at least 4 times sharper than what ground-based telescopes can achieve. Wide enough to survey a third of the entire sky over its mission. Most telescopes are built to zoom in tightly on one object at a time. Euclid was built to do the opposite, capturing vast swaths of sky in a single pass while still resolving fine detail within them. That combination has made Euclid remarkably good at stumbling into things nobody was specifically looking for. And in early June 2026, that's exactly what happened. A team of researchers at the Space Telescope Science Institute in Baltimore set out to study something specific: the internal motions of stars inside NGC 6397, a globular cluster roughly 8,000 light-years away in the southern constellation Ara. NGC 6397 is one of the 2 closest globular clusters to Earth, first documented by French astronomer Nicolas Louis de Lacaille back in 1752, a tightly packed sphere of somewhere around 400,000 stars, estimated to be about 13.4 billion years old, meaning most of these stars formed when the universe itself was still in its infancy, not much more than 1 billion years after the Big Bang. It's even bright enough to spot with the naked eye under good viewing conditions, despite sitting thousands of light years away. The team's actual goal was to trace how stars moved within that dense cluster using Euclid's data, cross-referenced with observations from the Hubble Space Telescope. But when they sorted the cluster's stars by brightness and color, building what astronomers call a Hertzsprung-Russell diagram, a standard tool that plots how bright a star is against its color and temperature, something jumped out that had nothing to do with what they'd set out to find. A gap. A narrow, clearly defined band where a specific group of low-mass red dwarf stars should have appeared in the data and simply didn't. Not a scattering of missing data points that could be waved away as noise. A distinct, statistically significant absence, detected at a confidence level greater than 5 sigma, meaning the odds of this being some kind of random fluke are astronomically small, comparable to the confidence thresholds physicists demand before calling something a genuine discovery rather than a coincidence. Massimo Grigio, the lead author on the resulting study, described the moment plainly. Globular clusters are ideal laboratories for studying stellar evolution precisely because every star inside one sits at roughly the same distance and formed at roughly the same time, which strips away a lot of the usual guesswork involved in comparing stars scattered across the galaxy. And in this particular perfectly controlled laboratory, a chunk of stars that should have been there simply weren't. Co-author Andrea Bellini put it even more directly. The discovery, in his words, was serendipitous. Nobody went looking for a gap. The gap found them. So what's actually causing it? Researchers do have a leading explanation, though it's one still being actively tested. The missing stars sit in a very specific mass range, somewhere around 0.34 to 0.36 times the mass of our Sun. At that particular size, red dwarf stars are believed to undergo an internal structural transition, shifting from having a partially convective interior, meaning heat moves through only part of the star via churning motion, to becoming fully convective, where that churning motion extends all the way through the star's core. That transition is thought to briefly and subtly alter the star's internal structure and its overall luminosity, and because relatively few stars spend much time actually passing through that specific transitional phase, they become statistically underrepresented at that exact brightness level. Picture it like a crowd of people walking at slightly different, constantly changing paces through a single doorway. At any given moment, you'd expect to see relatively few people caught exactly in the doorway itself compared to those clearly on one side or the other, That's essentially what's happening with these stars, just stretched out over millions of years instead of a few seconds. On a graph, plotting thousands of stars by brightness and color, that underrepresentation shows up as a visible gap, a genuine dip in the data rather than a smooth, continuous distribution. It's a compelling explanation, but researchers are careful to describe it as the leading theory, not a settled conclusion, because this specific gap had never been documented inside a globular cluster before. A similar feature had previously been spotted among stars in our own galactic neighborhood, using data from the European Space Agency's Gaia mission, but finding the same signature inside. A tightly packed, ancient cluster like NGC 6397 is new, and it opens a door researchers weren't expecting to walk through. And that door leads somewhere genuinely useful, because scientists can measure exactly where this brightness gap sits with very high precision, and they know precisely what stellar mass corresponds to that gap. They can use it as a kind of built-in ruler. Russell Ryan, another researcher on the team, explained that this allows astronomers to estimate the cluster's distance from Earth with a level of accuracy that's difficult to achieve through other methods, essentially turning an unexpected anomaly into a genuinely practical tool for measuring the universe. It's a neat reversal of how discoveries usually work. Instead of a new measurement technique leading researchers to an anomaly, the anomaly itself became the measurement technique. The findings were published in the journal Astronomy and Astrophysics, and they represent something researchers are already excited to test elsewhere. If this exact same gap shows up in other globular clusters, and current evidence suggests it could become a standard technique for measuring distances to some of the oldest, most tightly packed stellar systems in our galaxy. Systems that have historically been difficult to measure precisely using other established methods. Here's the thing, though. This wasn't Euclid's only headline-grabbing image in 2026. Just weeks later, on June 24th, 2026, ESA released what it called the largest, most detailed visible light image ever captured of the Milky Way's crowded galactic center. A 6-gigapixel mosaic built from 26 hours of observation across 9 overlapping telescope pointings, resolving more than 60 million individual stars. The image covers an area of sky roughly 22 times the size of the full moon, revealing dark molecular clouds, active star-forming regions, and the galaxy's densely packed central bulge in a single, continuous view. Buried inside that same image were 51 previously known planetary systems, along with roughly 60 additional exoplanets that had been detected before but never precisely measured, giving astronomers a dramatically improved read on their masses and distances. Scientists involved noted the data will also give NASA's upcoming Nancy Grace Roman Space telescope, launching later this year, a genuine head start by overlapping directly with one of its planned core survey regions. It's a genuinely staggering amount of information sitting inside a single unified picture of our galaxy's chaotic, densely packed heart. And earlier that summer, a separate team using Euclid's combination of wide-area imaging and sharp infrared vision announced the discovery of 31 previously unknown ancient quasars, extraordinarily bright, distant objects powered by supermassive black holes, dating back to the earliest chapters of the universe's history. For years, astronomers could only detect the brightest, rarest examples of this ancient quasar population, exceptional objects that offered valuable individual clues, but represented only a tiny sliver of what actually existed in the early universe. One of the newly found objects, catalogued as EUCL J172902.775 plus 641, DO 8D.1, sits at a redshift of 7.77, placing it among the most distant single objects ever identified, its light having traveled across nearly the entire observable history of the universe to reach us. Researchers describe this as the beginning of a genuine census of the early universe's quasar population. Rather than the usual handful of extreme, rare outliers, astronomers have typically been limited to studying. None of these discoveries, the star cluster gap, the galactic bulge mosaic, or the ancient quasars, were the original point of Euclid's mission. The telescope was built to map dark matter and dark energy across billions of light years, a slow, patient, statistical survey stretching across a third of the sky. But because it's designed to see so much so clearly at once, it keeps stumbling into genuine surprises along the way, findings nobody wrote into the original mission plan. That's really the through line connecting all of this. Euclid wasn't built to hunt for anomalies. It was built to survey everything methodically, with purpose. A missing patch of stars nobody was searching for, a galactic panorama containing dozens of previously uncharacterized worlds, a hidden population of quasars from the dawn of cosmic time. Every one of these findings started the same way. Astronomers pointed Euclid at something specific, expecting one particular kind of result, and instead found something that immediately demanded a second look, a new question, and in some cases, an entirely new explanation still being worked out in real time. Euclid's survey is still ongoing, with years of observations still ahead before its full map of the sky is complete. Researchers plan to make 52 separate observations of a single deep field alone over the coming years, a single early pass-through which already spotted 4.5 million galaxies. If the pattern established so far in 2026 holds, that means more unplanned discoveries are almost certainly still waiting inside data the telescope hasn't fully analyzed yet, hiding in the gaps between the observations everyone already expected to make. There's something worth sitting with in all of this. Euclid's core mission, mapping the invisible scaffolding of dark matter and dark energy across billions of light years, is slow, patient, and largely statistical. It doesn't produce dramatic single moments the way a targeted mission built around one specific object might. And yet, almost as a side effect of doing that job thoroughly enough, it keeps handing scientists exactly the kind of dramatic, unplanned moments those targeted missions are designed to chase. A missing patch of stars nobody was searching for. A galactic panorama containing dozens of previously uncharacterized worlds. A hidden population of quasars from the dawn of cosmic time. If you want to know the next time Euclid stumbles into something nobody was looking for, subscribe and turn on notifications, because based on this year alone, it's not a question of if, it's simply a question of when.